going to go over one example that was in the homework. Some of you might find it a bit challenging in terms of simplifying it. I don't remember the exact question, but this problem is similar to one of the homework questions. So the problem is use ratio test to show if the series n from 1 to infinity square root of n plus 2 times 10 to the power of n divided by n to the, let's just see, 200. Doesn't matter what it is, right? Just some exponent. Nothing. So we want to know if this series is absolutely convergent or divergent. So what we're going to do first is that we're just going to apply the ratio test, right? In the ratio test, we have to define a L. So define L equals limit n goes to infinity of an plus 1. So an plus 1 over an in an absolute value. So make sure you include the absolute value here. It's very important you include it. Now, what is an plus 1? I'm just going to put it in there. An plus 1 is just all the n become n plus 1, right? So that becomes square root n plus 1. But we already have a 2, so plus a 2 there. Times 10 to the n plus 1 divided by n plus 1 in a parentheses 200. So that's the an plus 1. And then we're going to divide by an, which is the given expression. So this is an. We're going to divide by that expression. So that's a square root n plus 2 times 10 to the n divided by n to the 200 in absolute value. The next step is to simplify anything that we can simplify, like multiply by the reciprocal or split the, for example, here we have 10 to the n plus 1 term, which we can separate it as 10 to the n times 10, right? We can do that. Now, be careful, the square root part, we cannot separate it. We can just write as n plus 3, we cannot separate that. Same thing in the denominator when we have n plus 1 to the 200, we cannot separate that. We just have to leave it the way it is. So limit n goes to infinity, absolute value, square root of n plus 3 times 10 to the n times 10 to the first power, and then divide by n plus 1 to the 200. Now I'm going to multiply by the reciprocal of the denominator, so that's the n to the 200 divided by square root of n plus 2 times 10 to the n. And now we can try to simplify 10 to the n. Right, that's it. Nothing else will cancel directly. So what do we do next? Now, remember that we try to take the limit, right? It's better to keep like expressions with a similar form together. For example, we have a square root here. We also have a square root in the denominator. It's better if we try to put them on the side together. And the n to the 200 power and the n plus 1 to the 200, maybe we can put them together. So maybe put those together. And now what about the 10? Well, the 10 is just a number, right? It's a constant. We can either keep it inside the absolute value or put it aside somewhere else. So that will give me, I'm going to put it on the left here. So that will be limit n goes to infinity. And like I said, I'm going to put the two square root parts together. So that's a square root n plus 3 divided by square root of n plus 2. And then in the numerator, we have n to the 200. So that's being multiplied. In the denominator, we have n plus 1 to the 200. We also have a 10, so I'm going to keep the 10 aside. So it should be absolute value of 10, but we know that 10 is positive already, so we don't have to write the absolute value. So we can just write 10 there. And then this 10, we can bring it all the way in front of the limit. So this 10, we can put it in front of the limit. It's just a constant. So what do we have? We have 10 limit times limit n goes to infinity. Now we have two parts. We have a square roots on the left and the n to the 200 and the n plus 1 to the 200 on the right. So what I'm going to do is I'm going to split the fraction as two fractions. So that becomes absolute value square root of n plus 3 over square root of n plus 2. Absolute value times absolute value. So when you split the fraction inside the absolute value, when you write as two expressions separately, you should keep absolute value on all of them. N to the 200 divided by n plus 1 to the 200. And the next step is that we can take the 2 square root part and write it as a 1 square root. So that's a limit n goes to infinity, absolute value square root n plus 3 divided by n plus 2, but now they are all underneath the same square root, not two separate ones. And what about the one that has 200 power? There's a couple of things you can do. You can either bring them together as a one expression underneath with the same exponent like we did with the square root. So here, so two things. One, you can write them as something to the 200 power, or you can just divide by n to the 200. So I'm going to show you the second way, but it really doesn't matter which way we take. So this is the easy way, just like the square root, but the second way is that we can divide by n to the 200 power. Now, some problems you might find it useful to divide by n to the 200 instead of putting it together as a one fraction with 200 as an exponent. But it doesn't really matter, it depends on the example. So here, the numerator just becomes 1. What about the denominator? The denominator becomes n plus 1 to the 200 divided by n to the 200 absolute value. So now we can put them together because sometimes when you put them together, it's make it easy to take the limit. But like I said, it really depends which one you prefer. It doesn't really, both are correct. So that will becomes 10 limit n goes to infinity. The first part is still the square root. The second part is 1 over in the denominator. And now I'm going to put it together as a single exponent. So that's a n plus 1 over n raised to the 200. The benefit of doing that is now we can split that term in the denominator as two fractions. So that will be 10 limit n goes to infinity, square root of n plus 3 over n plus 2. I'm sure you can take the limit of this square root times 1 over parentheses n divided by n is 1 plus 1 over n. So that's how we split the fraction there to the 200. And now we can take the limit of multiple terms, which we can take the limit of each term. So if we take the limit of the first term, if you don't see it, we can just divide by n in the numerator and denominator. And that will be 10 times when we take the limit of the square root. Underneath the square root, we get 1. So that's the square root of 1, just 1. And then if we take the limit of the second expression, the 1 over n, as n goes to infinity, 1 over n goes to 0. So the denominator there becomes 1 plus 0 to the 200 is 1. So again, you get a 1 there. So it ends up to be a 1, to be a 10.
Could you scroll down a little bit? No, to the bottom. Thank you.
Yeah. So it really depends. This is one way to write it, and it just keep in mind that we are taking limits, right? You try to take the limit of all the terms that's possible. When you take terms with a similar form, like same square root or exponent, you can always combine them together. Then it might make it easy to take a limit. And so now we are at the end, so we get the limit. The L is 10. So since L equals 10, which is greater than 1, right? By the ratio test, we know this is the given series is divergent. But I just want to use this example to show you a few tricks that, even though we begin with like a complicated series, but because some of the terms, when you put them together, you can take the limit easily. So this is so always try to put them together as much as possible, and then take the limit of each kind of section there. Any questions on this problem that I picked? It's not an exact question in the homework, I think, but you're going to have something similar to this. All right, I'm not hearing any questions here. Any other quick questions? I'm not going to spend too much time on the homework, so if you have a quick question from the homework, you can let me know. Maybe we can go a bit together now. Or you can ask them tomorrow during office hours, or at some point tomorrow during the lecture. That's okay too. Like I said before, definitely take a look at the homework problems, because the questions on the quiz will be very similar to the homework questions. Well, at least it covers the same section, right? Here is about one. Okay, Julie, go ahead. What's the question? So probably again use the ratio test. To determine the series, -8 to the n, divide by 2n plus 1 factorial. Okay, good. That's a good one. So let's just, I don't know what the n is, so let's just say n from 1 to infinity, right? The beginning value of n doesn't really matter. So we're going to use the ratio test again for this one. So I'm going to just begin with the definition. Define the L, which is limit n goes to infinity, absolute value. Just like before here, with the given expression is an. Okay, so n is going from 0. That doesn't really matter. So we're just going to follow the ratio test. So an plus 1, right? So that will be -8 parentheses n plus 1. and the divide by the denominator is 2n plus 1, that's in an, but now we have to change the n to n plus 1. So that would be 2 parentheses n plus 1. So that's the n become n plus 1. But then we also add a 1, right? That's already there, factorial. So that's a an plus 1, and then we're going to divide by an, which is negative 8 to the n, divide by 2n plus 1 factorial. Absolute value. So the next step, we're going to just do what we did, like multiply by the reciprocal of the denominator and expand. For example, we have a negative 8 to the n plus 1. We can expand that. The factorial in the denominator, we can just leave it there for now. Maybe we can simplify it as by distributing the 2 and then combine with the adding 1 at the end. So that will become limit n goes to infinity. The numerator is negative 8 to the n times negative 8. Right? And then the denominator, if we just distribute the 2 and adding 1, so we get 2n plus 2 plus 1, so that's a 2n plus 3 factorial. And then multiply by the reciprocal of the denominator, which is 2n plus 1 factorial, make negative 8 to the n. So now we can cancel out the negative 8 to the n. That's pretty good. And then we have another negative 8. We can leave it there for now until the next step, or we can bring it outside, right? So the negative 8. So note this one, if we want to bring it outside, that would become absolute value of negative 8. Just keep that in mind if we put it outside. So now let's look at what we have, and then we will try to simplify the factorials. So now we have limit n goes to infinity, absolute value 2n plus 1 factorial, divide by 2n plus 3 factorial. And then the negative 8, you can leave it in there or you can bring it outside. In this case, I'm going to just put it outside as absolute value of negative 8, which is positive 8. So whatever we bring outside of the absolute value, we have to make sure it's positive. Now, let's look at the factorial. So I'm going to write on the side here. So 2n plus 1 factorial, that's a 2n plus 1. And then we're going to decrease that by 1. So that's a 2n, it's the next term. And continue to decrease by 1 each time. So we get 2n minus 1, 2n minus 2. Obviously, that's infinite. I don't know how big n is, right? There's a lot of terms there. So that's all the way to multiply by 3, multiply by 2, multiply by 1. That's just by definition. What about this second term, the one in the denominator? This one, we can follow the same pattern by expanding it as a product. So that will be 2n plus 3. That's the first term. The next term is 1 less than it. So that's a 2n plus 2. The following term is 2n plus 1, 2n, 2n minus 1. As you can see, the rest of the pattern of the product is the same as the one above, and the times 3 times 2 times 1. That's what you have when you expand it. Now, if you look at it in the 2n plus 3 factorial, when we expand it, this part is exactly the same as the one above. So they're same, right? Which means that's equivalent to, if we use factorial to this, the one in the green box, it's equivalent to 2n plus 1 factorial. Because it's, when we write it as a product, it has the same expansion as 2n plus 1 factorial. So they're equivalent, which is very, very useful because now the denominator here, we can just write as 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. Now the factorial only applies to the 2n plus 1. It's not everything factorial, just the last term factorial. And now we can substitute into the limit. So the limit becomes limit n goes to infinity of 2n plus 1 factorial divided by 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. Now you kind of have to think, like, treat 2n plus 1 factorial as a one expression, not separate ones. And then multiply by 8 on the outside. This is 2n plus 1 factorial. This is also 2n plus 1 factorial. We can cancel them, give us a 1 in the numerator. So we end up with taking the limit as n goes to infinity of 1 over 2n plus 3 times 2n plus 2 absolute value times 8. 8 is just a constant, right? That's a 3. So now we can take the limit. You can take the limit separately by splitting the fraction. Well, you cannot split the fraction in the middle. Kind of have to just take the limit together. So the denominator, if we have n approach to infinity, so this part is approaching infinity. This part also approaching infinity. So the product of them will be infinity in the denominator. Can you pull out n or something from the parentheses?
Yeah, I see what Christopher's saying. I was taught in the math lab that, like, if you have that 2n plus 3, you're ultimately going to have the 2n plus 3, 2n plus 2, 2n plus 1, but then you're going to ultimately pull the n factorial out. Is that the wrong way to go about it?
That's not a wrong way to do it. It's not like it's not wrong, but it's not necessary. That's I don't see the point of doing that. And I don't know off my head immediately if Chris, that's a good point, but I have to look at it. I'm sure that's right, but I just have to double check later if that's the correct way to write it. Because factorial is something that you multiply a lot of terms together. Just have to be a little bit more careful when you try to factor some terms out of there. I'm sure that's correct, but I just have to double check. All right. But in this case, it's just not necessary because eventually you want the factorial in the numerator cancel with something in the denominator, right? Or vice versa. So in this case, as long as you can get some terms to cancel, you don't need to get to n factorial to cancel. You can just get any sort of factorial as long as they match and you can cancel them. That will be, that will serve the purpose. But that's a good point. I'll look into that. So now we just end up with 1 over infinity as we take the limit, which approaches 0. Right. But this is a good question. Hopefully that helps. I'll write down this. All right, I hope it helps. And any questions about this example or the one before? All right, I'm going to move on to the new material. If you have any other questions, feel free to come see me during office hours. Like Aiden said, it's the Mac is really helpful. So if you go there, you're going to benefit a lot from them. You can find the information of the Zoom link on the website. All right, so I'm going to talk about 11.9 today, which is, so if you recall that last time we talked about power series. So today we're going to write functions in terms of power series. So representation of functions as power series, which power series n from 0 to infinity of Cn x to the n. So we're going to take functions, write it like that. We don't know what Cn is, but maybe we can find them. For example, a function like 1 over 1 plus x to the 7, can we write it as some power series n from 0 to infinity of Cn x to the n, or maybe some equivalent form as power series, right? What's the benefit of doing that? The benefit is that if we can find the power series representation of some given function, we can integrate it or differentiate it as if we are integrating the power series or differentiating the power series, which is a lot easier in some sense. So how do we find it? Well, let's consider a simple example. So consider the series 1 plus x squared plus x cubed, and continues, right? This is a series that we can write as n from 0 to infinity of 1 times 1 times x raised to the n, right? This is a geometric series. If you think about from 1 to x, we multiply by x. From x to x squared, we multiply by x. So we have a common ratio. So r equals x. So that's a geometric series. But it's with the x as a ratio, not a number. It's a little bit different from what we have seen before. But we do know, so for r equals x, or maybe absolute value of r equals absolute value of x, for that's less than 1, if the ratio, the absolute value of the ratio is less than 1, the series x to the n from 0 to infinity is convergent. That's what we already know, right? If the ratio is if the absolute value of the ratio is less than 1, the series is convergent. Well, if that's the case, if the ratio is less than 1, then we can find the sum of that series. So sum, so this the sum here, x, this series has the formula that's really nice, which is a over 1 minus r, which is a is the first term. In this case, the first term is 1. The r is x, so 1 over 1 minus x. Right, so that's this gives you the sum of the geometric series if the ratio, absolute value of the ratio, in this case, absolute value of x is less than 1. If that's the case, we can use this sum formula. How do we know x is less than 1? In this case, well, we know that in order for the geometric series to be convergent, the ratio has to be less than 1, right? The absolute value of the ratio has to be less than 1. So we just pick this. That's what this means for this condition. But we basically saying like we're picking x to be less than 1. Is this going to be on the quiz next week? It's not going to be on this week's quiz. So let me write down not on quiz tomorrow. So the reason I'm using this special series is to show you that if we have absolute value of x is less than 1, then we can always write the series using 1 over 1 minus x. It goes the other way too, which saying that we can write 1 over 1 minus x. In this case, I'm going to use a capital X. And we can write that as series n from 0 to infinity, capital X to the n. And this series is convergent for absolute value of x, capital X, is less than 1. So if we take the function 1 over 1 minus x and then write it as a series, sort of going backwards, and then we know that this series will be convergent when this x with absolute value is less than 1. So that's a very important, like a special example that we can use to find the power series of more functions in this type. But keep in mind that here we have the subtraction, so that's very important to notice. So that's a subtraction there. How do we use this? Well, for example, now the example we have above, I had 1 over 1 plus x to the 7. This example we can write as power series. And the way we do it, we just use the special example I'm boxed above. The 1 over 1 minus x is equal to sigma capital X to the n. So what we're going to do is that we're going to take this expression that I'm looking for as power series. I'm going to write as 1 over 1 minus negative x to the 7th power. That's the first step. You turn it into a subtraction. You turn it as 1 minus some term in the denominator that will look similar to the part that's given. So this will be similar now. And in this expression I wrote down here, we can just imagine that capital X in the previous boxed equation is equal to negative x to the 7. We can just use substitution directly. So here, capital X is equivalent to negative x to the 7. So that means this fraction, this rational function, I can write as sigma n from 0 to infinity. In the box one, I have capital X to the n, but now the capital X is negative x to the 7. So I get negative x to the 7 to the n. So that's the power series representation. And then we can simplify that by splitting the negative x to the 7 as negative 1 to the n, and negative x to the 7 to the n, write it as negative 1 to the n times x to the 7 to the n, with n from 0 to infinity, which becomes sigma n from 0 to infinity negative 1 to the n times x to the 7n. So this is the power series representation of the given function 1 over 1 plus x to the 7. So the trick we use is you take the denominator, you write it as a 1 minus some term. That's the capital X. Now, what does it look like? Well, if we want to know what the power series look like, we can just expand it. So we can expand this by just plugging n value, like different n values. So plug in 0. So we get negative 1 to the 0 is a 1. And x to the 7 times 0, which is x to the 0's power is also 1. So when we put n equals 0, we get 1. And we add, when we put 1 there, so negative 1 to the 1 is negative 1. And the x to the 7 times 1 is x to the 7. So we get minus x to the 7. And if we put 2 there, we get negative 1 squared is positive 1. X to the 7 times 2, that's x to the 14th, and so on. So that's the power series. That's equivalent to 1 over 1 plus x to the 7.
So the thing you have circled is what we were supposed to end up with?
Over here, yes. It's a habit that mathematicians do. Like you probably think, oh, why can't I leave it over here right after I plug in the negative x to the 7? We don't like to write like this. We like to separate the negative 1 from the rest, and also just try to simplify the exponent as much as possible. Because if we have negative 1 separated, we immediately know that from here, we know it's an alternating series. If you didn't have it separated, it's not obvious. So that's one. Any questions on this example?
So when you plug in n equals 0, how are you just getting 1? Like I'm just a little bit confused.
So if you put n equals 0, you get negative 1 to the 0 power times x to the 7 times 0. Negative 1 to the 0, any number to the 0 power is always 1.
Oh, got you. Okay.
Right, so that's a 1. This is also x to the 0, right? It's 1.
Sweet. Thank you.
Now, what about the radius of convergence? Well, previously in the one I'm writing in purple at the top here, we know that the 1 over 1 minus x is convergent for absolute value of capital X is less than 1, right? Which means this one I just found, this series is convergent. So maybe let me write down here. So this series that I have 1 over 1 plus x to the 7 equals series n from 0 to infinity, negative 1 to the n, x to the 7n. This series is convergent we're going to follow the same pattern there. The previous one, we have capital X in absolute value is less than 1. So in this case, it will be absolute value of capital X is negative x to the 7. That's the substitution we used earlier. For this capital X to be less than 1. So that's a condition for convergence of this series. We take this fact that in this example, capital X is equivalent to negative x to the 7. So we're just going to use, instead of capital X, we use negative x to the 7 in absolute value. So that will just become x to the 7. Absolute value is less than 1. We can drop the negative, which eventually it's become just x is less than 1. The 7's power doesn't really matter because when we take 7's root on both sides, then we still get 1 there.
And how do you know negative x to the 7th is less than 1? Are we just saying it is? Or is there some way to prove that?
Well, it's based on this part I'm boxed in purple, right? So this series, the relationship is true, and the series we found is only convergent when we have absolute value of x is less than 1. And in this example I'm giving, I don't have capital X, right? But what I have instead is that I have negative x to the 7, which is equivalent to the capital X from above. Therefore, if we want the series to be convergent, the capital X, in this example, negative x to the 7, has to be less than 1 when we take the absolute value.
I'm still a little bit confused because the x in the example is less than 1. The 1 plus x to the 7th is less than 1. I'm just a little bit confused by that still.
Are you confusing about this part? The one that
I'm confused on how the negative x to the 7th is still less than 1.
Because when I applied the formula above in the box, like that's how I end up with the power series, right? So I take the given series, the 1 over 1 plus x to the 7, I write it as 1 over 1 minus x to the 1 minus negative x to the 7.
Mm-hmm.
So here I have negative x to the 7, but in the one that I have above, I have negative capital X. So that means capital X is equivalent to negative x to the 7. That's why I have this relation down here, right?
So if we have a negative and like our in front of the x, like down below, like the negative x to the 7th, it's going to be less than 1.
It just whatever. So any expression in the example you're working on, anything that's equivalent to capital X, that has to be less than 1.
Okay.
In order to find the convergence, the radius.
So it's always going to be less than 1 if it's in that x spot.
Correct. If it's equivalent to capital X, whatever that expression, that part has to be less than 1 when you add an absolute value.
Okay, that makes a lot more sense. Thank you.
Yep. And then the rest is about simplifying, trying to find what x is. So we found out that absolute value of x is less than 1, which you can think about as absolute value of x minus 0 is less than 1. If you remember that, this is like an x minus a absolute value less than r, and r equals 1 in this case. So this 1 here is what we call the radius of convergence from what we talked about last time. So r equals 1 is radius of convergence. Because we have absolute value x minus 0 is less than 1. Now the second example I have is we have x cubed over x plus 2. And we want to take this and find the power series representation. So again, I'm going to take this series, try to make it looks like at some point 1 over 1 minus capital X, and then we can apply the same power series we had above. So how do we do that? Well, we have a numerator which is not 1, but that's okay. We can just put aside the x cubed in the numerator. So we have x cubed times 1 over x plus 2. Right? But then we still have issues with the new denominator because here we want a 1 to begin with, but here we have x plus 2. Well, we could just switch them and then make it looks like x cubed times 1 over 2 plus x. It doesn't help us too much, but it's a little bit, right? Because we want a 1, now we have a 2. Maybe we need to make the 2 a 1, so we can take out a 2 from the denominator. So we have x cubed times 1 over 2 times 1 plus x over 2. So now we have 1 plus something, but we want 1 minus. And the 2 in the denominator, we can just put it aside. So now we have x cubed over 2 times 1 over 1 minus negative x over 2. This expression looks exactly like 1 over 1 minus capital X.
So you can't have that 2 in the bottom, like you have to pull it out to get a 1 plus or a 1
Correct.
minus.
1 minus. You always, if you want to use the one I boxed in purple directly, you have to have 1 over 1 minus.
So it's always going to have that minus as well, like that subtraction.
Correct.
Okay.
So this part is equivalent to capital X we had before. And the one that in front of it, don't worry, that's just there. We can include it in the power series later, but for now it just stays there. So now the one that I'm boxed in purple here, in blue here, that's 1 over 1 minus X. Well, I mean capital X, so that's a 1 over 1 minus negative X over 2. So now I can write x cubed over 2 times the one in blue, that becomes sigma n from 0 to infinity. It used to be capital X to the n, right? If you go back to this, that's just capital X raised to the n, but now it's negative x over 2 raised to the power of n. So let me write down. So capital X equals negative x over 2 here. And just like before, we can separate the negative. So that becomes x cubed over 2 sigma n from 0 to infinity. We get negative. You can also bring the 2. So you get negative 1 to the n over 2 to the n, or negative half to the n. Or you can keep it with x times x to the n. That's what we get when we separate all 3 of them. So that's pretty good, right? We're getting close to the end. But because we have x cubed over 2, we can actually, in front of the sigma, we can actually bring it inside the sigma. So that will become sigma negative 1 to the n divided by 2 to the n times x to the n. Then we're going to multiply by x cubed over 2, the one that we had in front of the sigma. Now we put it inside. So that becomes sigma n from 0 to infinity. Negative 1 to the n is just negative 1 to the n. 2 to the n multiplied by another 2 in the denominator. So that's a 2 to the n plus 1. X to the n times x cubed. So that's x to the n plus 3. After we put them together. So this is the power series representation of the example we had which is x cubed over x plus 2. We can write it as power series n from 0 to infinity, -1 to the n over 2 to the n plus 1, x to the n plus 3.
So I'm a little confused after you found x. What do you do after you find x?
After I find the capital X, I'm using the fact that 1 minus capital X is equal to power series n from 0 to infinity, capital X to the n. So after I find capital X, I'm basically like, this part looks like this. Therefore, if I want the power series representation, I can just find the corresponding capital X part, which is negative x over 2. And then I can just put into the right-hand side, give me the power series representation. So literally take the what capital X is supposed to be and put it into the right side. That's how I end up with this expression below, right here. And then the rest is about simplifying, separating the -1, separating the 2, and then the x. So this one I'm writing in blue, so that's an important sort of conversion that we use here, that converting 1 over 1 minus x into a power series. So in both examples, I've been using the same conversion there. And then later, we're going to talk about more general case that you cannot translate it into 1 over 1 minus x. How do you find the power series? There's other ways that we can do that. Does that help? Any other questions? What about finding the radius of convergence? We're going to follow what we did in previous example. We know that the series on the right here, this series converges if capital X, in this case, capital X is negative x over 2, but I'm going to, maybe I should put here, if negative x, if absolute value of capital X is less than 1, right? That's when it converges. But in this example, we don't have capital X. We get negative x over 2. So we want this part to be less than 1. From there, we can try to find the radius of convergence, because from negative x over 2 absolute value is less than 1. That's a condition for the series to be convergent. From here, we can try to write as x minus a less than r there. So that's the same thing as absolute value x over 2 less than 1. And then we can multiply by 2 on both sides because 2 is positive. So absolute value of x less than 2, which you can write as x minus 0 less than 2. And then the 2 here is what we call radius of convergence. And we get it by manipulating the capital X, absolute value of capital X less than 1 expression. with the correct substitution of capital X, obviously.
I'm sorry, could you explain how do you find that again?
So we use the fact that this series, the series capital X to the n, this series is convergent if capital X in an absolute value is less than 1. That's what we use. And in this example, after I find the series, we know that it will only be convergent if absolute value of negative x over 2 is less than 1, because negative x over 2 is equivalent to capital X. So this series I found is convergent if the absolute value of negative x over 2 is less than 1, right? And how do we find the radius of convergence? We're just going to take that inequality and manipulate that, try to find out the R there. So all I did is I dropped the negative because it's in the absolute value, and I multiply by 2, and that was absolute value of x less than 2, which I can write as x minus a, absolute value less than R. And if you recall from previous lecture, the R is what we call the radius of convergence. In this case, I is equal to 2. But basically just take the number directly. So you kind of have to think about, remember those all together. It's not just 1 over 1 minus x equals sigma x to the n. You also have to know that that series in this expression, it's only convergent when capital X in an absolute value is less than 1. You have to remember all of them together. That because the absolute value of x less than 1 is important to help you find out when the series is convergent or the radius of convergence. The one boxed in purple there, that's helpful to find the power series, but the one that highlighted in red there, that's helpful to know when the series is convergent. So the next part is that we can differentiate and integrate power series. Differentiation and integration. So let me write down a couple definitions first. So if power series, and then I'm going to go through a couple examples. If power series Cn x minus a raised to the n for n from 0 to infinity has radius of convergence capital R greater than 0, then the function we write using power series, function defined by power series, so f of x could be any function. If we can write as power series, as n goes from 0 to infinity, Cn x minus a raised to the power of n. This function is differentiable on interval a minus r, a plus r. So the interval of convergence, if you recall. Since it's differentiable, that means we can find the derivative. And number one, the derivative of f, we can write as f prime of x, which becomes sigma n from 1. So maybe let me highlight it. This is a 1, not a 0. N from 1 to infinity, Cn, just like we normally take the derivative, we bring the power, bring the exponent in front and the minus 1. So there'll be Cn times n times x minus a to the n minus 1. And 2, if we try to integrate the function, so integral of f of x dx, we can just integrate the x minus a to the n part. So that will become sigma n from 0 to infinity. Cn, when we integrate x minus a to the n, we add 1 to the exponent, so n plus 1. But then we have to divide by the new exponent, so divide by n plus 1. Maybe I should put it here, divide by n plus 1. Doesn't matter where we put it. So when you differentiate, you basically differentiate only this part, but then you still keep the sigma under the Cn there. So that's why you end up with this expression. When you integrate, you integrate that only x minus a to the n part, you end up with x minus a to the n plus 1 divided by n plus 1. Just like we did with power functions before. Now I'm going to explain a little bit why we have n equals 1 to the infinity when we take the derivative. Well, let me just expand f of x. So expand f of x. So n equals 0, we get c0 times x minus a to the 0, which is 1. We just get c0, a constant, plus c1. And when we put 1 there, so we get c1 x minus a to the first power, plus c2 x minus a squared, and more terms coming after. But when we take the derivative here, f prime of x, when we take the derivative, the c0 is a constant, so that becomes 0. Plus, when we take the derivative of x minus a, we get 1. So we get c1 times 1, just c1. Plus, the next term will give me 2c2x minus a and the plus, right? So in the derivative, as you can see, the first term always becomes 0 because we take the derivative of a constant c0, so that always becomes 0. So in the derivative, we always begin with c1, not a c0. Oh, I forgot something. We add a c here, capital C. So that's why that's why here we get a n from 1 to infinity, not n to the 0. Not n equals 0 to infinity. So that's the difference, because the c sub 0 term, it's gone now because it becomes a 0 when we take the derivative. So we begin with c1, not c0. And in the integral, we always have an addition of plus c, right? When we integrate something, we add a constant c there. You can try to think it in that way. All right, so that's the derivative and the integral of a power function, of a function in power series. And I want to note that, so for the derivative and the integral, so for f prime of x in power series and the integral of f of x dx, the radius of convergence are still the same, just the same R we had for the power series. So the power series of f of x has the radius of convergence R. When we take the derivative, it's still the same R for radius of convergence, or when we integrate, it's still the same. Because we still have x minus a absolute value less than R. So any questions about taking derivative and the integrating? Just be careful with the derivative part. The n is not from 0, n is from 1. And then when we integrate, that's a plus a c at the end. So here's an example. So we're going to find the derivative d dx of Bazel's function, which is a special function used a lot in high-level physics. J0 of x equals sigma n from 0 to infinity, -1 to the n, x to the 2n divided by 2 to the 2n times n factorial squared. It looks complicated, right? But when we take the derivative, we only focus on the x part, the x minus a. In this case, we don't have x minus a, we just have x to the 2n. That's the only part that we focus on. The rest, they're just coefficients. So if we take the derivative of J0, we end up with the sigma stays, the -1 to the n stays, denominator 2 to the 2n, again, those are just numbers, right? They stay. And the n factorial doesn't depend on x, they also stay. The only thing that's different is x to the 2n. We just take the derivative of that directly. So that becomes, bring the exponent in front, so that's a 2n times x to the 2n minus 1. And obviously I'm making a mistake here, because remember that in the derivative, the constant begins with c1, not c0, so n goes from 1 to infinity, not 0 to infinity. And the only thing that's different is this part. We just take the derivative as if we only take the derivative of 2n, x to the 2n. Any questions on this? Why did you write n equals 1? Well, like I said, when I write down the definition for the derivative and the integral, right? For the derivative of f, so for f of x is from sigma n from 0 to infinity. When we take the derivative, we have n from 1 to infinity in the derivative. Like I explained earlier, when we take the derivative of f of x, the c0 becomes a 0 there. So the first term of the derivative begins with c1, not with c0. So that's why the n will come from 1 to infinity, not from 0 to infinity. So here's the second example I have. So the second example is express the function 1 over 1 minus x squared as power series and find radius of convergence. Well, you can try. So this is a 1 over 1 minus x squared. You can try to take this and then write it as 1 over 1 minus capital X. Right? And it's not easy. It's very, I would say it's very difficult to do that because you have a square in the denominator. Right? Even though it looks like a 1 minus x in the denominator, but has a square. And by the way, I want to point out that you probably think, oh, can I write as a 1 over 1 minus x squared? I mean, the reasoning is not wrong, right? But if you find the power series for the 1 over 1 minus x, you end up squaring a series which, if you want to write this as a series, it's very difficult to do because you're squaring a series. It's you basically take infinitely many terms, you multiply them together, and then try to. So you get 1 plus x squared, and multiply with 1 plus x squared. And if you want to FOIL every term, and then try to write it as a series using sigma notation is very difficult. So that's why we don't just square the series. It's a very bad idea to square the series. So what do? We can't put it into 1 over 1 minus capital X directly. So the previous trick doesn't work. Well, the trick here is to use the fact that the derivative of 1 over 1 minus x is equal to 1 over 1 minus x squared. That's the trick that we're going to use. We're going to use that the derivative give you this function that we want. So the one that we're looking for, 1 over 1 minus x squared, ddx of 1 over 1 minus x, we can just take the derivative of 1 minus 1 over 1 minus x. That's a power series. That's a sigma n from 0 to infinity, x to the n. Right? We just take the derivative of this series, so that becomes just the derivative of the x to the n. So that becomes sigma n from not 0, from 1 to infinity, n times x to the n minus 1. So this is the power series representation of 1 over 1 minus x squared.
How did you go from 1 over 1 minus x to sigma infinity n equals 0 to x to the n?
So from here to there, that's using the fact that we had earlier. So 1 over 1 minus capital X equals sigma capital X to the n from 0 to infinity, which we have seen before. This is exactly the same because the lowercase x, it's equivalent to capital X.
Oh, okay, I'm with you.
Yeah. So I use the trick that we did in previous examples. Now, what about the radius of convergence? So to find the radius of convergence, in this example, we're going to focus on the series that we found, which is this one. This is the series we had before we take the derivative, right? What is the radius of convergence of this one? Well, we know that when we apply the trick, so we know that this series is convergent for absolute value of x is less than 1, right? Because capital X in absolute values has to be less than 1 in order for the general case to be true. In this case, it's just lowercase of x has to be less than 1. And the r equals 1 is the radius of convergence before we take the derivative. Before take derivative. Right? But if you remember what I wrote earlier, when we find the derivative of a function, or when we integrate it, the radius of convergence stay the same. They don't change. So the r equals 1, even after we take the derivative, we end up with this new series. So after the derivative, the radius of convergence is still the same, r equals 1. It doesn't change in the process.
How did we determine that r is equal to 1?
Say it again.
How did we determine that r is equal to 1?
Well, we determined that so consider the series in the green box, right? That series is convergent for absolute value of x is less than 1. Because you can think about this is a geometric series, right? When does the geometric series converge? It converges if the ratio, in this case, the ratio is this x here. If the ratio is less than 1, or absolute value of the ratio is less than 1, that's when geometric series is convergent. And in this case, will be absolute value of x is less than 1. And that 1 on the right-hand side is just the radius of convergence. Because this inequality, you can see that's the same thing as x minus 0. Absolute value is less than 1. So x minus a less than r. It's a form. And r is the radius of convergence. If you write in the correct form, and r is corresponding to 1 there.
I thought r has to be less than 1 though.
It's not.
I guess it's
Okay,
like that.
so here I'm talking about capital R, which is the radius of convergence. It's just a value. It's not an inequality. Now, if you talk about the common ratio of a geometric series, that's a lowercase r. That has to be less than 1. But the lowercase r, the ratio of a geometric series is equivalent to x in this case, which is less than 1 if you add the absolute value. But when we talk about radius of convergence, we talk about capital R in the form of, in the inequality x minus a absolute value less than r. This r is what we call the radius of convergence.
So the r we determined is from the x of n, and there's nothing in front of the x, so it's just 1.
Correct. There's nothing in front of the x. It's just 1 times x in an absolute value less than 1.
Gotcha. Thank you.
Yeah. If there's something in front of x, then you have to divide by that number or multiply by the denominator to make it x minus a. So here's a second example. Well, I don't know how many examples already, but this is another example. So we're going to express natural log of 1 plus x as power series. And also we're going to find the radius of convergence. So again, natural log of 1 plus x, it's difficult to just write as 1 over 1 minus capital X. it's difficult to put into this form directly. Right, so that doesn't work. So the hint here is to use the fact that natural log of 1 plus x is equal to the integral of 1 over 1 plus x dx. So that's the hint we're going to use. Because 1 over 1 plus x, we can try to find the power series, and we can integrate it. So natural log of 1 plus x is equal to integral 1 over 1 plus x dx. This expression in the middle, I can try to use a trick to find the power series. So that becomes integrating this one I'm boxing green, that's a 1 over 1 minus negative x. Remember that we always want it to be 1 minus something in the denominator, dx. And that becomes integral. Now this part, I can, using power series, so that's sigma n from 0 to infinity, negative x to the n dx. And the series in the middle here, so let me just box it before I move on to the next line. This one is convergent if absolute value of negative x is less than 1, because that will be important later when we try to find the radius of convergence. But let me continue. So now we need to integrate this. So when we integrate it, if we go back, when we try to integrate a function, we just integrate the x part, the x minus a part. So here, when we integrate this, we got to do something first. We got to split the -1 from negative x. So let's split this. So that's a integral sigma -1 to the n x to the n. So now we can just focus on the x to the n when we integrate n from 0 to infinity dx. All right, could you have switched that earlier? I'm not sure what you meant switch, which part earlier.
So like get it in the x minus a form instead of having it be 1 over 1 minus negative x. I switched it and did 1 over x minus -1 because that's in the x minus a form.
No, don't do that, because the reason I'm putting it in this form, because I know that 1 over 1 minus capital X is equal to sigma capital X to the n. That's the equation I want to use to write the 1 over 1 minus X using power series. So if you have X minus -1, then it's not the same. You got to be very careful there. It doesn't change anything, but when you applying the equation directly, you will run into problems at some point. And then now let's integrate x to the n. So we still have sigma n from 0 to infinity, -1 to the n. It doesn't change. But x to the n now becomes, when we integrate, we get x to the n plus 1. But then we have to divide by the new exponent. So divide by n plus 1. So that's the integral, but plus a constant c, which we will find at some point. But for now, let's just keep the c there. So any questions until this point? So the next part is to find what the c is. Well, to find c, we can just set some x value and then try to set both sides of the equation So the left side, we have natural log of 1 plus x. The right side, we have this series plus c. So we can set x equals 0. The left side, we have natural log of 1 plus 0. The right side, we have sigma n from 0 to infinity, -1 to the n, 0 raised to the n plus 1, divided by n plus 1 plus a c. Right? Just plug in x equals 0 directly. And the 0 to the n plus 1 is always going to be a 0. And a 0 times anything is always a 0. So this series become a 0 because part of it is 0 and then the rest is being multiplied with 0. So this will just become a 0. And then the left side, natural log of 1 plus 0 is just natural log of 1, which we also know that's a 0. So natural log of 1 equals c, 0 equals c. So c equals 0 at the end. And what do we end up with? We just end up with, I'm going to write it here, natural log of 1 plus x is equal to sigma n from 0 to infinity, -1 to the n, x to the n plus 1, divided by n plus 1. We don't have a c there. Because the c becomes a 0 when we set x equals 0 to find c. Any questions there? The next thing I'm going to show you is to find the radius of convergence, right? The series that I have before integration, the one I'm writing in green here, we know it's convergent if absolute value of -x is less than 1. So before integration, we have absolute value of -x is less than 1. And from here, we can just drop the negative. We have absolute value of x is less than 1. You can write this as x minus 0 less than 1. So that means the 1 is the r value. So r equals 1 is the radius of convergence before integration. That's what the radius of convergence is. But after the integration, we end up with this series. It doesn't change the radius of convergence. So after integration, there's the same radius of convergence there. R is still 1. It doesn't change in that process. As you can see in those two examples, we can find power series representations of functions that you cannot use the simple trick we used. You kind of have to use integration or differentiation, try to find a new power series.
So the after integration, when you're getting that r, you're still just looking in front of that x.
Say it again.
After the integration for you're getting that r, is it that equation that's just pointing the arrow to it, and is it that thing in front of the x?
No, I get this I equals 1 after integration. I get it directly from here because it doesn't. The radius of convergence doesn't change after we integrate. So whatever the radius of convergence we found before integration from that series from here, that will be the same radius of convergence later after the integration.
So how do you know it didn't change though? Like what part didn't change? Because we didn't have a c?
The radius of convergence doesn't change in the process. That's just definition.
Okay.
All right, I'm going to go through another example, and then we can end the lecture today, just to give you more practice of this type of questions. There'll be a homework, maybe sometime Thursday or Friday, that will give you more practice on this. So the next example is to express function f of x equals inverse tangent of x as power series. Right, again, if you're not familiar with inverse tangent of x, well, if you're familiar, whether you're familiar with it or not, it's very difficult to take that and write as 1 minus some capital X form. It's just like a natural log or the previous example we had. Not easy, probably impossible. I don't know. But there's a fact that we can use. So hint, use the fact that d dx of inverse tangent of x, which is a 1 over 1 minus plus x squared, 1 over 1 plus x squared. That's what we're going to use. Which means if we integrate both sides, we get inverse tangent of x is equal to integral 1 over 1 plus x squared dx. Of course, it's adding a c, but it doesn't matter because later on we're going to have another c added. So just combine them. So for now, this will be the one that we use. So inverse tan of x is equal to integral 1 over 1 plus x squared dx. And again, remember that we want to have something 1 minus capital X squared, because then we can directly apply this equation to find the power series. So we have to change the denominator, just like the very first example we did. So 1 over 1 plus x squared, we can write as a 1 over 1 minus negative x squared dx. The negative x squared here is equivalent to capital, sorry, that's not square, just 1 over 1 minus x. So this part is equivalent to the capital X in that expression. So that becomes integral. Now we can use the power series sigma n from 0 to infinity negative x squared to the n dx. That is just substitute the function I'm integrating with power series. And again, at this point, I'm going to write down this series is convergent if absolute value negative x squared is less than 1. We may or may not need it later to find the radius of convergence. And the next step is I'm going to separate the negative 1 from the x squared, the negative x squared. So I have integral sigma n from 0 to infinity, negative 1 to the n, x to the square, x squared raised to the n, x to the 2n dx. Because now when I integrate, I will only think about x to the 2n. I don't need to think about negative 1. It's a constant. So the next step is to integrate. So we get sigma n from 0 to infinity, negative 1 to the n. Integral, when we integrate x to the 2n, that becomes x to the 2n plus 1, right? We add 1 to the exponent and divide by the new exponent, which is 2n plus 1. Don't forget to add a c at the end. Any questions until this point? So this is the first part is like we did before, is 1 over 1 plus x to the 7, but the next part is just integrating the power series by using the definition. Now the next step to find C, again, I'm going to use the trick that we had from previous example. We're going to set x equals 0. The left side, I have inverse tangent of 0. And to the right side, I have sigma n from 0 to infinity, -1 to the n, 0 raised to the 2n plus 1, divided by 2n plus 1, plus a c. We have 0 raised to any exponent, that's always going to be 0, right? And a 0 multiplied by any number is always 0. So this series, every term there become a 0. So the whole series becomes 0 when you add all those zeros together. And what about inverse tangent of 0? If you think about the angle, so which angle, when you have tangent, when you take tangent of the angle, you get 0. And the angle is 0 here. So we get 0 equals C in this example. It's not, the C is not always 0, right? Frank is right. So it's 0. So, but keep in mind that the C at the end, not always 0, depends on what the left side function give you when you plug in 0. You know, if it's like different number other than 0, that will be the C value. So don't always assuming C is 0. So at this point, what do we have? We have inverse tangent of x, the one that we're looking for. We want to find a power series, and then we found it, which is sigma n from 0 to infinity, -1 to the n, x to the 2n plus 1, divided by 2n plus 1. And then we don't have a c to add. So that will be the power series representation for inverse 10. Any questions on this and how I end up with this last step? So the process is that the first step, obviously, you know, so the hint is very useful, right? The one that we're looking for is difficult to find the power series directly, but if we think about the derivative of it or the integral of some function, then it's become easier. So that's sort of the important part, is the hint. And then the rest is about, like, you know, you're finding the power series for the function you want to integrate, do a little bit separation there, separate the -1, and then you integrate the power series, and that will give you the new series that we're looking for. All right, I have 1 minute. I'm going to quickly finish the radius of convergence. So again, so before we integrate, we found out a power series, and we know that the series is convergent if absolute value of -x² is less than 1. This is before integration. And from there, I can write absolute value of x² is less than 1 by dropping the negative. It's inside the absolute value. And if I square root both sides, I get absolute value of x less than 1, which is the same way if we write it as absolute value x minus 0 is less than 1, which tells me that the 1 here is the R value, the radius of convergence, before integration. What about after? After the integration, we get a new series. Instead of finding the radius of convergence from here, we can just see, because earlier we had radius of convergence is 1, that should be the same. So after integration, we still have R equals 1, because the radius of convergence doesn't change when we integrate. from the definition.